In the previous approach, we end up by making the same recursive calls repeatedly. For example, if we want to calculate the gate lengths at 5 and 3 and gate lengths at 5 and 4, we end up by calling the gate lengths at 3 and 2 twice. So to generate the entire fifth row, which is zero-based row indexing, we would like to have two gate lengths at 3 and 2 4 times. So if we want to avoid to making the same recursive calls repeatedly, it makes sense to store the result of the intermediate recursive calls for our later use. So in our second approach, let's try the dynamic programming algorithm. First, we just use a simple memoization caches, results of the deep recursive calls, and it will provide a significant savings on runtime. So let's try to turn our algorithm in Python. First, we set class solution. Then we define the double underscore initialization, double underscore, and self parameter. Then we have to use self.cache, which is the dictionary. And then we can define the gate names, which have self and row and call. Then we set key is the opposite and ordinate of the row and call. Then we say if the self.cache.get key, if it exists, we just read it in our memory, so we just return itself self.cache.get key. Then if it is didn't exist, we just have to calculate it. So it divides to two kind of case. One of is a computed value is 1, assigned by 1. If the row is 0, means the first row, or the call is 0, means the first number in the row, or row is call, means the last element of the row. Then, so this time we assign 1 to computed value. So if it is not else, we have to calculate it by self dot get name row minus 1 and call minus 1, which is the upper left side, and the self dot get name row minus 1 and the call don't change, so it is just up of it. Then after we calculate it, we just assign it self.cache add key, which is computed value. So we just assign the value to the cache add key. Then we return the computed value. Then we define our main function, define get row, which have self parameter row index, and which is integer, and it return a list of integer. Then we set an empty list and to hold the value, to hold our result, and we set for loop for I in range from 0 to row index, remember to +1. Then so every time at each for loop we write a number into it by the append by self dot get num and row index and I. Then after we done, we just return the answer. So that's it. Let's write example print solution dot get row, let's say 5. Let's say 5. So which is 1, 5, 10, 10, 5, 1. Yes, we did it. But it was noting that generating a number for a particular row requires only 2 numbers from the previous row. Consequently, generating a row only requires numbers from the previous row. Thus, we could reduce our memory footprint by only keeping the latest row generated and use that to generate a new row. Let's try to build algorithm in Python. First, we just declare a class solution. Then we define a get row, which have self-parameter row index, and it is integer. Then we return a integer list. Then we set the preview list to hold our value, which is default by one element, which is 1. Then we set a for loop for I in range from 1 to row index plus 1. Then we set a current list to hold our current, which is start from 1 for default. Then we set inside loop list inside it is for j in range from 1 to I. Then every time we append the element into the current, which is the previous at j minus 1 plus previous at j. Then after we're done, we can just append 1 to the last element. So the last element is 1, right? Then after we're done, we can assign the current the value to the preview. Then we are done. We just return to the preview. So we can print an example solution dot get row. Let's say 5. Yeah, it is 1 5 10 10 5 1. Yes. Let's analyze the complexity. The time complexity is O of k squared because we just use a simple memoization, so it will make sure that a particular element in a row is only calculated once. So let's assume that our memoization cache allows us constant time lookup and updation like a hash map. So it will take constant time to calculate each element in a Pascal triangle. Since calculating a row requires calculating all the previous rows as well, so we will ending up by calculating the first row have 1 element, the second row have 2 elements, the third row have 3 elements, and the k plus 1 row have k plus 1 element. So the summarization is k plus 1 multiplied by k plus 2 divided by 2, asymptotically equal to k squared elements for kth row. Let's talk about the space complexity. The simple memoization would need to hold all of the elements, which is 1 plus 2 plus 3 plus blah 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 plus k plus 1, which is k plus 1 multiplied by k plus 2 divided by 2 elements. So in the worst case, that will require O of k squared space. And the second approach, which saves space by keeping only the latest generated row. So we need only O of k extra space, so other than O of k space required to store the output. So the space complexity is O of k plus O of k, which is asymptotically equal to O of k.